Hi learners, in this mode, first we will start how much syllabus we covered up to last lecture. So we covered for the IT, BTech final year IT, we covered what is a digital image processing, examples of fields that use digital image processing, fundamental steps in digital image processing, components of an image processing system, image sensing, image acquisition, image sampling, quantization, basic relationships between pixels, and introduction to Fourier transformation. And next, something one dimension domain frequency domain one dimensional Fourier transform and its inverse. Very briefly we discussed, and very briefly we discussed DFT and its inverse. Okay, and in this board we will discuss some spatial transformations, and we also discussed in the previous sessions arithmetic and logic operators. Okay, and these concepts you will get in your lab programs and in the next units also. There I will explain you elaborately. And next, coming to the syllabus of MCA, we covered image acquisition, image model, sampling, quantization, relationship between pixels, distance measures, connectivity, image geometry, all the geometrical operations we have seen, photographic film, and next we will discuss histogram in this in later videos, and we covered arithmetic and logic operations, pixel or point operations, size operations also we covered. A brief discussion of mean median is covered in the last video, and a brief discussion of DFT we covered, Fourier transformations we covered. Okay, and in the next syllabus also uh, we will get about these in detail. I'll explain there in detail. Now, in this part, we will discuss intensity transformation and spatial filtering. Okay, very important. We reached the important concepts in the image processing. Okay, so whatever we processing upon the image, it reflects on the based on the intensity, and we are transforming something into an input into output, and where we are transforming by applying what kind of operations. So transformation operations we will apply, and some other spatial filtering operations we will apply. Now coming to the spatial domain versus transform domain. So here you can observe we are discussing about the domain. So an image is placed within a domain, and we are comparing the whether it is a spatial domain or it is a transform domain. We are comparing these two. So for that, first we have to know what is a spatial domain. An image is placed, we know, by the space of x coordinate and the y coordinate. So here our image is placed. Suppose this is the image. Then this is the spatial domain. We calling it is the spatial domain. And all these points are the intensity values. So this is the image plane. And image plane is itself, and it is directly process the intensity values of the image plane. Okay, so within the spatial domain, we are whatever the operations we are performing upon the image are directly processed on intensity values of the image plane. Okay, this is spatial domain. Now coming to the transform domain. What is meant by transform domain? So suppose we are transforming some image T with this original position into something rotated position, like in this way. Suppose. So this is the input image and this is the output image. Then this input image is transformed into some other by applying some other operation, rotation, whatever it may be, is transformed. Okay, so here the process of transform coefficients. So on what coefficients? This is same, but the coefficient here is changed up to something angle, transformed the angle. So the process is upon the coefficients, not to directly process the intensity values of the image plane. Okay, so image is here only, but we are transforming this image into some other direction or other place like that. So the image within the plane is transformed, not like a not look like as a original one. Okay, then that is the transform domain. So within the spatial domain, we are applying the process directly on to the intensity values of the image, but it is plane itself. But in the transform domain, we are applying upon coefficients. Okay, so here coefficient x may change here into something like w. Here xy coefficient is changed, transformed into wz coefficient. So it may be the f of x comma y, the original image, and it may be the transformed image t of w comma z. This is the difference. Now, how we process spatial domain? How? So for that, this is representing the output image. So after performing the spatial domain process, means directly processing upon the intensity values of the image, but within the plane itself, then we are applying some T operator which is defined over neighborhood points of x comma y. Okay, and this is the original input image. We know we are representing original input image is representing with the xy coordinate, and the function is f of xy, right? So spatial domain process means we are applying T operator. This T operator is defined over x comma y neighborhood points. Then this is giving the spatial domain process output image. So f of x comma y is the input image, we know that, and g of x comma y is the output image, we know that, and t is an operator of f defined over a neighborhood of point. Now we will see some spatial domain processes. How we are applying spatial domain processes. Here I already told you some x coordinate and the y coordinate are there. With this two-dimensional plane, we are representing the image within this plane. So this is called the spatial domain. I already told you. And this is the image which is representing F. And this image is 3 by 3 neighborhood of x comma y. So this is the input image pixel x comma y, our f input image. For this we taken 3 by 3 neighborhood values. So neighborhood values, the image is represented with the matrix form. Okay, so in this way we will represent the image within the spatial domain. Then after applying some intensity transformation function upon the spatial domain process f, then we will apply some r coordinate function by the operator t. Okay, then the output intensity transformation function is representing with the s. And how we do this intensity transformation function, how we will generate the output intensity transformation function by applying some t operator, means this is the example for the contrast stretching. So when we apply the contrast stretching function, then our output S function is look like this. This is the output. So here this is the input at a 0 level, and we are applying T of R intensity transformation function. This is the S. And when we apply thresholding function on the same input image, then we will get this type of output S function. Okay, so T operator on thresholding function giving this kind of S output, and contrast stretching function giving this kind of S function output. Now so for the contrast stretching it look like this, and for the thresholding it look like this. In the same way, some basic intensity transformation functions are here. Look at this. So suppose we want a negative, then the output S function is in this way. The output is in this way. Okay, and suppose we are applying some intensity transformation function which is log, then our S function is we will get a S function in this way. And suppose we are applying nth root intensity transformation function, then we will get this kind of graph. And identity function, if you apply this kind of graph, we will get. And nth power, suppose we are applying nth power intensity transformation function, we will get this kind of. And inverse log, if we apply, then we will get the graph in this way. Okay, so all these graphs curves are scaled within the ranges of L minus 0 to L minus 1. So these are representing intensity levels R, and these are representing output intensity levels S. Okay, then some other negative intensity transformation functions we have. Those are giving this kind of graphs. So for the negative, this is the graph, and for the output intensity value, here it is just a L minus 1, and if it is a negative, then here it is L minus 1 minus R. The input intensity value is the R and L minus 1 is the range. Then we will get for the log, this is the curve, and for the nth root, this is the curve, identity, this is the curve, and the power, this is the curve, inverse log, this is the curve we will get. Now see, upon the image, suppose we apply log transformation. Okay, so this is the Fourier spectrum. Then if we apply some log transformation upon this Fourier spectrum, then this is the resultant one, output one we will get after log transformation. And so see this is the original digital mammogram image, and if we apply some negatives upon this image, the negatives transformations, then this whole is a lessened by small lesion. Okay.
So, in image negatives means the operations are these. This is the equation for the negative image negatives. S is equal to L minus 1 minus R. We are calculating the R is the intensity value of the input image, and S is the intensity levels after transformation, after applying this image negatives, these curves with these intensity values, the operation. So S is the output intensity values. And then when we have seen this image negatives, so if we are applying these, then we will get the particular lesion of the image, a smallest part we can identify. Then coming to the log transformations, these are log transformations I already shown you in the previous in this board previously. So with this log transformations, by applying C log 1 plus R transformation, the log transformation, then we will get with this input intensity value. This is the this is the curve, inverse log curve, and for this is the output intensity levels we will get. So by applying this, we will get the log transformation and application. Here it is example image. So by applying the log transformation upon this Fourier spectrum, we will get the resultant intensity values of this input. This is the output.
Now I'll show you another type of transformations apart from log transformations and other transformations. This is power law, that is nothing but gamma transformation. We know this is the symbol of gamma. So by varying various values for the gamma, we are doing some transformations upon the image. When these are our input intensity values and these are resultant output intensity values uh, after applying gamma transformations. So whenever the gamma value is equal to 25.0, the curve is in this way. Whenever the gamma is equal to 0.10, then our curve is look like this. We will get this result. And the transformation equation, the gamma transformations, nothing but power law transformations. Equation is S is equal to C into R to the power of gamma. Okay, here C is a constant value. Most of most of the cases C is equal to 1. Maximum cases C is equal to 1. Okay, so S is the output intensity value, R is the input intensity value, input image intensity value, S is the image intensity value, and here the transformation depending upon the gamma value. Now I'll show some differences before the image, original input image, and after applying gamma transformation upon a image, and where we are applying these gamma power law transformations. I'll show you. Whenever we see the input and output differences after applying transformations, then we will get the clarity how to use, where we apply all those things. So this is the example for the gamma transformations. All in this board, all we discussing various types of transformations. So this is the original image. Okay. So observe here uh, some intensity ramp image is this one. In this input picture, this is uh, inten- intensity ramp image, and if this is the original input image, and if we see this intensity ramp image in the monitor, we will see in this way. Observe this shading here. It is appearing in this way in our monitors. Okay, so this is the original image, and this is we are viewing in the monitor, on the monitor. Okay, and for this original image, we are correcting the gamma correction. Corrected one means we are applying the gamma operation. How much gamma operation? So this is the formula. S is equal to C into R power gamma. Okay, here I already said gamma is varying with the various values, these many values. Then here we applied the gamma value 2.5. Okay, then for the gamma value 2.5, this is the curve we are getting. After applying this gamma value upon this, here C is equal to 1, R is the input intensity value. Then for this transformation, we got this image. Okay, and if we see this image on our monitor, we will get the output image is this. So if we observe something, the shading here, then that will be corrected in this output image in this way. So after applying gamma transformations, we will get the resultant images like this. So this is the application oriented models. When we observe the before transformation and after transformation of each transformations, gamma transformations, log transformations, like that, then we will see the difference, and we came to know where we apply to which image, which transformation we can apply. All these we came to know. Then this is another example for the gamma transformations, and this example for this example we need some, actually no need. If we know this about the CRT, which is very well explained in the computer graphics CG subject,
if we came to know, then we can easily understood about this example. Here, this is the input image. In this input image also, we are applying gamma transformations, and this is the image of cathode ray tube, nothing but CRT. Okay, our inside the TV monitor. Okay, the monitor and the TV, all those are built up with the CRT, cathode ray tubes. Okay, and about the functionality and about the CRT very well is explained within the CG computer graphics subject. You came to know because this is the extension of the subject computer graphics. So, this image example is given in your textbook. So, for the CRT devices, the intensity to voltage response, that is power function. We know this is the power function. This is the power, the gamma value. Okay, so intensity to voltage response, that is a power function with the exponents varying from approximately 1.8 to 2.5. This is the original image, and this image we can see on our monitor in this way. So CRT is producing some intensity to voltage responses, cathode ray tube. So for the input image, for the intensity to voltage CRT, it is changing. We are viewing in this way. And after applying gamma transformations between the gamma values 1.8 to 2.5, the power function 1 by 2.5, then this is the output image originally, and this is we are viewing in the on the monitor. And the best example, best application for the gamma transformation, where it is very important one in our real life, real time application, is here. This is the MRI scan reports. This is the MRI scan report, magnetic resonance image. Okay, magnetic resonance image, original image of the fractured human spine. So when a spine is fractured, uh, uh, we are taking MRI scan, magnetic resonance image. Then this is the input image MRI giving for the fracture of the human spine. Then for this, we are viewing on the computer in this way, and this is the fracture part after applying gamma transformations. So how much gamma transformation we are applying here is, we know S is equal to C into R power gamma, and gamma is varying, but the C is equivalent to 1, we know. So here the gamma value we are using 0 0.6, 0 0.4 and 0 0.3, okay, respectively. So with these values, the output of the MRI scan are this and this. These two are the outputs. And next, another gamma transformation application, real-time application, is this one. This is the original courtesy image given by satellites. Then we are applying gamma transformations. How much the power function of the gamma is 3, 3.0 and 4.0 and 5.0 respectively. With those, the resultant applied gamma transformation output is this one and this one and this one. Okay, depending upon the gamma power function 3.0, 4.0, 5.0, these are the resultant ones. So, in this board, we covered the topics spatial domain was transform domain. So, in the spatial domain, how the image, original input images look like, and what types of operations, transformations we will apply upon spatial domain, then how it is transformed. And we compared the spatial domain to transform domain for, and we also discussed spatial domain processes, and then we discussed some intensity transformations. What are the basic level intensity transformations are available? Then image negatives we discussed, and we have seen the examples how the image negatives giving the output results, and also we seen the examples of log transformations after applying log transformations, and what are the different types of real-time environment requirements for log transformations where we are applying. Also, we seen gamma transformations. Then, in the next lecture, we will cover piecewise linear transformations. Then, we will enter into histogram, important one. Okay, learners, we will see in the next board.